Now what does this mean? This means independent and identically distributed. So for example, if x1 is a random variable that has expectation value, say mu, and variation as sigma squared, that's a typical letter. Those are the typical letters that you assign for average and variance. The reason you use mu is because mu is a Greek letter M, so M stands for mean. Okay, so this is the expectation you write as mu, and this sigma, this is not letter 6, or it's actually Greek letter sigma, which is English letter S. S for standard deviation. Okay? And by definition, standard deviation is the square root of the variance, so standard deviation squared is the same as the variance. Okay? That's why we use these letters. And being IID means their averages will be the same. Their standard deviation will be the same. These two should be same. And not only that, their probability distribution function will be exactly the same. Okay? As an example, you can think of like throwing the dice twice. Then if x1 is the number that you get in the first roll, and x2 is the number that you get in the second roll, they are distributed in the same way. They follow the same probability distribution, right? Yes?
Second equation, is that supposed to be v of x?
Oh, thank you. V of x. Thank you. Okay. So assuming this, what I want to show you is the following. What is x1 plus x2? Well, expectation values are linear. You can just take them separately. So it'll be 2 mu. Another way to look at this is if you take the average it will be over 2, which is just mu. So let's see how this plays out in an example. Let's say x1 and x2 are both the outcome of a die when you roll. Okay. What's the expected value when you roll a die?
1 over 6.
No, that's 1 over 6 is the probability of getting one of them. But what's the average value of the number that you get? It's 1 through 6. So what's?
3.
No.
3.5.
3.5, right? Yeah. 3.5 would be the average value, right? Now, what if you? So what does that mean? That means that if you roll a die several times, like 1,000 times, and you take the average of all those values, you're going to get 3.5. You'll be closer to 3.5. On the other hand, let's say you have a red die and a blue die, and they behave exactly the same way. Okay, so x1 is the number that you get from the red die, and then x2 is the blue one, and then you just throw them individually 1,000 times. You record their values separately, okay? And then every time you throw, you're going to take the average of those values. So if the red comes out as 1 and the blue comes out as 5, 1 plus 5 divided by 2, that's 3, so that's the one that you record. You keep recording these values 1,000 times and you take the average. What do you get? Same thing. Because it's not going to change much, right? So that's what this computation does. So, I mean, sometimes if you just do the math, you don't know what it means. I want to make that clear. But that's not so interesting. That's not so interesting. What is interesting, though, is the following. This one let's see, this is e of x1 plus x2 squared minus e of x1 plus x2 squared, right? And then that's going to be e of x1 squared plus 2x1 x2 plus x2 squared minus, this one we know this is 2 mu, right? We just did it, 2 mu squared. Okay, now let's see, e of x1 squared, e is linear, so you can just apply to 3 different terms separately. Okay. All right, but let's look at this one. See, Vx1 is e of x1 squared minus e of x squared, and that is equal to x1 squared. That is equal to sigma squared. And because I know that this is mu, I see that e of x1 squared is going to be sigma squared plus mu squared. See, this one's mu, right? And you have mu squared. And because these are independent and identically distributed, what you get in the second one, e of x2 squared, it's going to be the same thing. So I can say this is sigma squared plus mu squared. This one, 2 can come in front, but e of x1 times x2, we just proved that if 2 things are independent, you can just make it as a product, right? So this is e2 times e of x1, x2. And then this one, because it's, we just know that it's the same thing as that one, it's sigma squared plus mu squared minus 4 mu squared. And then notice that this is mu, that's also mu, so it's 2 mu squared. Okay, let's see if you follow the calculations. If you simplify this, what do you get?
2 sigma squared.
Yes. Everything else cancels, right? You just get 2 sigma squared. Is that okay? 2 mu squared plus another mu squared. How many mu squared? 4 mu squared, but you're subtracting 4 mu squared. They go away, and then you just have 2 sigma squared. All right? So that's actually surprising. You might not think that's surprising, but let me write it like this to make my point. If you have v of x1 plus x2 divided by 2, then this 2 comes in front. Oh no, not that, but 2, 1 over, whatever you have as a product that comes out as a squared. Because you can see that I deleted the formula, but to get the, here. The formula has a square in there, so if you have any constant multiple there, it comes out as a squared. Is that okay? So it comes out as 1/2 squared. But then what is this? This is 1 over 4 times 2 sigma squared. So that means 1/2 sigma squared is what you get. Okay? So, here's my punchline. If you have 2 identically distributed independent random variables, x1 and x2, and let's say you just try to do the trial, get the number from that experiment, and then you just keep taking their averages, record them, and then if you have like thousands or millions of values, now take their average. What do you get? The average is the same. Okay? But what's happening to the variance? The variance of individual ones were sigma squared, but the variance of the average is half of the sigma squared. Okay. What does variance measure?
Spread.
How much is spread, right? So this is like one thing the hedge fund companies do. Right? They have portfolios. Right? So imagine that you're working in a stock market where they only have two tickers, only two stocks. Okay? Stock A, stock B, that's all. Okay? And they don't have any correlation. They just go up and down, who knows, right? But in this uncertain market, you're trying to build a hedge fund company where you want to guarantee that you're moving with about the same amount of average, but you want to make sure that when you lose, you don't lose too much, and when you win, you don't win too much, so that you have like a bit more stable financial system. Okay? What do? Instead of going all in for A or B, what you do is you make a portfolio of half of A and half of B. Now what's going on? You're tracking this, right? Half of A and half of B. What happens then? See, if sometimes they might both go up, sometimes they might both go down, but there will be other cases, because these are independent, there will be cases where one goes up and the other goes down. When the other goes up and this one goes down. So in those cases, the average will be more stable, right? So if you have two random variables that you take averages of, then they don't go up and down so much, giving you less variance. Does that make sense? And that's how hedge funds make money. They can make portfolio and say, oh, we can secure your funds. You might be worried that one day you'll suddenly lose all your money because the stock market crashes. Don't worry, we have this system where we can reduce the variance. It's hard to actually increase the average. That requires like good timing to sell this and then buy this other thing. That they might need a lot more research, and sometimes they might pay more money in research than what they earn. So it's not certain. But what definitely works because of the math is that if you have two independent random variables, just take the average, you have less variance. So this is a very important thing to know for random variables here. And this is going to show up in so many different ways. Now, let me try to generalize this. I just want to simplify things just by using two of them, but you can do the same exact math, just more work, for the following. If x1, x2, all the way up till xn are IID, independent and identically distributed things, okay, with expectation value as mu and v of x as sigma squared, then you have then E of x1 plus da 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 xn divided by n. If you take the averages of all these random variables, you get the same exact mean. It doesn't change. Okay. However, if you take the variance, it does change. What does this become? It will be sigma squared divided by n. Okay, which means that the standard deviation of x1 plus da 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 xn over n is sigma over square root of n. This is the most important thing you have to understand. Okay, so we're going to be using that a lot. All right.